Okay, by now we have learned that a current carrying wire can create a magnetic field. And now here we will see a moving charge can also create a magnetic field, which is explained by Biot-Savart law. According to this law, magnetic field created by a moving charge is equal to mu0 over 4 pi, which is the constant, Q V cross R hat over R square. Q is the charge of the moving charge. V is the speed of the moving charge. R hat is the distance unit vector of moving charge. And R is the distance from moving charge to the point that we want to calculate the magnetic field. For example, here, this is the moving charge, and we would like to calculate a magnetic field at this point. So from moving charge to this point is the R vector. So it is the distance between these two. If you would like to calculate the magnitude of magnetic field, this is the equation. I mean, this is a cross product, so that's why when we are writing the cross product for V and R hat, this is equal to the magnitude of V, the magnitude of R hat, which is 1, and the angle between them is sine theta. So that's why this equation will give you the magnitude of the magnetic field. And here, as you can see, for a cross product, both quantities are vector. V is a vector, R hat is a vector, and the resultant will be still a vector, which is the magnetic field. So what is the importance for this cross product? The magnetic field will be perpendicular both vectors. So magnetic field will be perpendicular to speed, and magnetic field will be perpendicular to the radius vector. So this is the magnitude. For the direction of the magnetic field, we will use right-hand rule. How you will do this? You will point your thumb in the direction of speed, in the direction of V. The magnetic field vector will be perpendicular to the R and the V, and it will point in the direction in which your fingers curve. So you will put your thumb in the direction of V and curve your finger. So you will see that your magnetic field, the direction of your magnetic field at this point will be in this way. This is perpendicular to R. This is perpendicular to the plane of the V. So in another words to say, magnetic field vectors are tangent to the circles drawn about the charged line of motion. For this. So in this question, there is a positive moving charge and its speed is out of the page. And what is the direction of magnetic field at this point? So put your thumb in the direction of V, which is out of the page, your right thumb. And when you curl your finger, the direction of your finger will show at this point downward. So that's why the answer should be B. And here we will see that if you put a moving charge in the vicinity of magnetic field, then you will see that this magnetic field, existing magnetic field, will exert a force on this moving charge. For example, this blue arrow shows a magnetic field, which is existed magnetic field before we put the charge here. And then you bring this positive charge in the vicinity of this magnetic field. And we know that this magnetic field, existed magnetic field, exerts a force on this moving charge. And this force is given by this equation or by this law, which is Lorentz force law, which is equal to Q times V cross product B. V is a vector, B is a vector. And finally, since this is a cross product, F will be on the moving charge. It will be also vector. So this F vector will be perpendicular to V. F vector will be perpendicular to V, and F vector will be perpendicular to magnetic field. So for a cross product, since the angle between, since we take the angle between speed and the magnetic field as sine, if velocity vector and magnetic field vector are in the same direction, the angle between them will be 0 and the sine of the 0 will be 0. So for this reason, for the first part, the force exerted on a moving charge by this magnetic field will be equal to 0. What about the second one? V is in the direction of, the green arrow is the velocity, the blue arrow is the magnetic field. And now how we will find the direction of the F, again from right-hand rule. You can apply the same rule as we did in the previous slide, or you can also find direction in a different way, which is much more easier. It is up to you which one you feel easy. For this one, what you do, you put your fingers in the direction of V, and you will bend your fingers towards the direction of the magnetic field, which means that put your four fingers in the direction of the V, and then curve your fingers in the direction to the right, in the direction of magnetic field. And the thumb will show you the direction of the force. So if you do it for this second example, you will see that F is pointing into the page. So for the third one, the velocity vector is to the right. So put your four fingers in the direction of V. And the magnetic field is into the page. So curve or bend your fingers towards the magnetic field, which means that towards into the page. And then the thumb will show you that F points upward. In the last example, the first three were positive charge. For the negative charge, it will be different. First of all, you are going to find the direction of F for a positive charge, and then you will take the opposite of it, which means that assume that this is a positive charge. So for a positive charge that moves to the right and the magnetic field is into the page, as in here, the force was upward, right? So since this is a negative charge, we will take the reverse of this direction. So which means that it will be downward. So this is the difference between positive and negative charges. And here let's do practice. There are several examples. Find the direction of force on a negative charge for each diagram shown. So what we are gonna do, since all of them are negative, first of all, let's find out what is the direction of magnetic field for a positive charge. And then we can take the opposite of for a negative charge. So for the first example, V is out of the page. So put your fingers, let me change this to the pen. Put your fingers in the direction of out of the page, and the magnetic field is downward. So which means that bend your forefinger in the direction of magnetic field downward, and you will see that your thumb will point to the right. So this is the force, direction of the force for a positive charge. Since the question is for a negative charge, we will take the reverse of it. For a negative charge, the force will be the reverse of positive charge. For the second one, velocity is pointing downward, so put your fingers in the direction of velocity, and magnetic field is into the page. So bend your forefingers into the page, and you will see that the force for a positive charge will be to the right, F positive. So for a negative charge, it will be to the left. For the third example, the velocity vector is into the page. Put your finger into the page, and the magnetic field is to the right. So bend your fingers towards magnetic field to the right. So your thumb will show downward. F positive. So for a negative charge, it will be F negative. And in the fourth one, put your fingers in the direction of V, and magnetic field is upward, right? So bend your fingers in the direction of magnetic field, which is upward, and then your thumb will show you F is out of the page. F plus, for a positive charge, it is out of the page. So for a negative charge, it will be into the page. So in the fifth one, the velocity vector and magnetic field are anti-parallel to each other, which means that their angle, the angle between them is 180. So sine of 180 is equal to 0, which means that F for a positive charge and for a negative charge for both of them will be equal to 0. In the last example, put your finger in the direction of V, which is to the left. And then your magnetic field is out of the page. Bend your fingers out of the page, and your thumb will show you the direction of the force, which is upward. F, this is the F for a positive charge. For a negative charge, it will be downward. Okay. Oopsies. And in this slide, we see a cyclotron motion, which means that a charged particle moving perpendicular to a uniform magnetic field executes a cyclotron motion. So here the magnetic field, existing magnetic field is into the page, right? And you bring a moving charge in this magnetic field, and this moving charge is perpendicular to the magnetic field. So in this case, it will undergo a cyclotron motion, which means that it will make a circular motion. In this case, at each point, if you look at the force, you will understand why it undergoes a circular motion, because force at each point will point towards the center. For example, here, this is V, the direction of the velocity. Put your fingers in the direction of velocity, and the magnetic field is into the page. So curve your finger into the page, and your thumb will show you direction of the force. At this point, it is here, the force is to the right, and here, direction of F again is into the center. So that's why it will make a circular, uniform circular motion. From Newton's second law, we know that F is equal to mass times acceleration, right? For a circular motion, acceleration is V squared over R. So that's why centripetal force that we have learned before is equal to mv squared over R. But here, since a moving charge is located in the vicinity of magnetic field, still the magnetic field will also apply a force on this moving charge, which is given by this, as we have done in the previous slide. It is equal to Q V cross P, but the angle between V and the magnetic field is 90 degrees, so sine 90 is equal to 1. This is the magnitude, Q times V times magnetic field. So these two forces are equal to each other, and from here, when you find out R cyclotron is equal to the distance from center to the moving charge is equal to mass times speed over Q times magnetic field. We know that frequency is equal to speed over 2 pi r. So if you plug in into the equation here for the frequency, we will calculate cyclotron frequency as QB over 2 pi m. And okay, and here there is an example. Please work on this question, and we will upload the solution for all examples or for all whiteboard problems. And here let's talk about mass spectrometer. Mass spectrometer is an analytical instrument used to identify the various molecules or various atoms in a sample by measuring their charge to mass ratio, which is Q over M. And here the sample is ionized, so the positive ions are accelerated through a potential difference delta V between S1 and S2. So here it's negatively charged plate, this is positively charged plate, so the electric field between these two upward, the red arrow shows the direction of the magnetic field. And here there is also a magnetic field which is out of the page. So for a moving positive charge towards this potential difference, due to the electric field, there will be an electrostatic force in the direction of electric field, which is upward. So here between the plates, F electrostatic upward. So the positive charge is moving towards right, so the direction of V is to the right, which is V, and the magnetic field is out of the page. What is the force acting on this moving charge due to the magnetic field? Put your finger in the direction of V and curve your finger in the direction of magnetic field, which is out of the page. So the force will be downward. If magnetic field will be downward, and for the molecule to go straight between those plates, this F electrostatic is equal to, should be equal to F magnetic field. So from this relation, you can also derive an equation for V in terms of electric field and in terms of magnetic field. These two Q will cancel out. So the speed will be in terms of magnetic field and the in terms of electric field and magnetic field is equal to E over B. And then once the charge particle moves straight between the plates, it enters a uniform magnetic field, which is out of the page in this case. So what will happen? This magnetic field lines bends the ion into a circular trajectory. Why? We just learned it, cyclotron motion. This is the direction of V, and V is perpendicular to the direction of magnetic field. So that's why those charged particles will undergo a circular motion. But after just a half circle, as in here, they either strike the wall, or they strike, or they pass through a small opening right here through the detector. As the accelerating voltage is slowly increased, different ions will reach the detector, so that's why they will be measured. And by this way, we can use this spectrometer to identify atoms and their concentration in a sample of materials. And here we see that if you put a current carrying wire in the vicinity of magnetic field, this magnetic field will apply a force in this current carrying wire. And this is the equation for this force. It is current times L, the length of the current carrying wire, times magnetic field. This is current, and this is length, and this is the magnetic field. Again, there is a cross product, so we will apply the same rule to find the direction of force. So put your fingers in the direction of L. Look at here. This is current carrying wire. The direction of the direction of the L will be the direction of the current. So your fingers will point upward. So magnetic field is into the page. So curve your finger into the page towards the magnetic field. So force on this current carrying wire will be to the left. Here we will learn the magnetic field of parallel current carrying wires exert a force on each other. So on the left hand side, we see that the current in both wires, wire 1 and wire 2, are in the same direction. And on the right hand side, we see that the current in both directions are in opposite way. So this is wire 1, the current is to the right. This is wire 2, the current is to the left. So for the left-hand side, since each wire is carrying a current, each of them will create a magnetic field that we have learned before, because we have learned that a current carrying wire will create a magnetic field. So for the first wire, if you put your fingers, if you put your thumb, your right thumb in the direction of the current, so curl your finger around the wire, you will see that there will be an inward magnetic field at the location of second wire. So that's why those magnetic field which is into the page at this point is created by current 1. What about the magnetic field created by current 2, second wire? So put your thumb in the direction of I2 and curl your finger around the wire, and you will see that at this point where the wire 1 is located, the magnetic field is pointing out of the page. So each dot is the magnetic field, which is B2, created by current 2. So that's why this magnetic field created by second wire will apply a force in the first wire that we have learned from this equation. And at the same time, this magnetic field into the page created by current 1 will apply a force in the second wire, again by using this equation. Let's think about the first wire. The force is equal to current, which is I1, times L, the length of the wire, times B2. B2 is the magnetic field created by current 2. So instead of B2, we will write the equation that we have learned from the first slides. If you remember that the magnetic field around a current carrying wire is equal to mu0I over 2 pi r. So what is this B2? It is mu0 constant I2, because this magnetic field B2 is created by wire 2, so that's why we use I2, over 2 pi r. R is the distance from current to the location that we are looking for the magnetic field, which is the distance between these two wires, and we know that it is d. So that's why once you rewrite this equation, the force on wire 1 due to the second wire will be equal to mu0 L I1 I2 over 2 pi d. If you apply the same formula for the second wire, you will get the same equation as a magnitude. It will be same, but their direction will be different. The direction of the force on first wire is downward, and the direction of the force on second wire will be upward. So that's why we see that they attract each other. On the right hand side, we see that in wire 1, the current moves to the right. In wire 2, the current moves to the left. So which means that currents are in opposite direction. So that's why the magnetic field created by the first wire at this point, which is B1, is into the page. And at the same time, the magnetic field, which is created by second wire at the location of first wire, will be again into the page. So that's why at each point between the wires, and outside of the wire, the magnetic field everywhere will be into the page. So that's why once you find out the direction of the forces acting on both first wire and the second wire, you will see that for the first wire it will be upward, for the second wire it will be downward, and as you can see here, they are repelling each other. So this is another whiteboard problem. Please work on those questions and we will post the solution. There is another one. Again, same thing. Please work on it and then we will post the solution. So in the, not this one, yeah, here. And here we will talk about Ampere's law. Ampere's law is very helpful method to calculate the magnetic field. And we had learned a similar law when we talk about electricity. If you remember, to be able to calculate electric field of charge distribution, we had learned Gauss's law, and it made our job very easy to calculate many surface charge distributions. And here we will learn a similar law, which is Ampere's law, to calculate the magnetic field of current distribution. So according to this law, the line integral of a magnetic field, this is a line integral of magnetic field B dot ds, around a closed loop, this is the closed loop, is proportional to the current, which is I enclosed current, that passes through the area enclosed by the loop. This is the loop. So that's why if you take the line integral of B magnetic field and set it equal to mu0 times I enclosed, which is the current inside of the loop, you can easily calculate by using the symmetry. You can easily find out what is the magnetic field. And here, del cross B, it is the curl of magnetic field. It is also proportional to current charge density. It is current density, J, that passes through the area enclosed by the loop. Again, line integral means we have learned, or you have learned it in the calculus 1, when you talk about integral. Assume that there is no magnetic field around. So here there is a line from initial point to the final point. Line integral of, there is a curved line between initial and final points. What we do, we divide this line into many small pieces with a length of delta S. So if you take the integral of this delta S, which means that, what does it mean? To be able to find out the length of this curve from an initial point to the final point, what you will do, you will sum them up of all those delta S, right? So the summation of delta S will be equal to the integral of this small segment. So we call it is line integral. So here we see that the integral is an easy way to sum them up, all those small segments. So now assume that your line is in the vicinity of magnetic field. The blue arrow shows the magnetic field. So that's why we are looking for the line integral of the magnetic field. What we do, we take dot product of B with delta S at each point, at each segment. So when you sum them up, all those segments, it will be equal to integral of B dot ds. Since it is a closed curve between initial and final point, we say that it is a closed loop. And this line integral will be equal to mu0 times I enclosed, the enclosed current in this closed loop. So here there are two examples. In the first one, the question is, what is the line integral of B from initial point to the final point for two cases? So the line integral of B from initial to final point, B dot ds. Right? B is constant, so just put it outside of the integral. The integral of ds from initial point to the final point, assume that this length is equal to L. So the integral of ds, which means that the summation of all this small ds segment is equal to L. From 0 to, what is this point? 50. And this is equal to, B is 0.1 Tesla, times the length of this L from initial to final point from 0 to 50 is the hypotenuse of 50 is the height, and this is the adjacent side. This is also 50. So just calculate the hypotenuse here, and then it will be in square root. Just change centimeter into meter. 0.5 square plus 0.5 square. So you will find that the line integral of this magnetic field will be equal to 0.071 Tesla meter. What about the second one? This is the line integral. So this is the line between I and F. This is the magnetic field. So what is B dot ds? They are perpendicular to each other. For a dot product, the angle between magnetic field and the length vector, ds vector, will be 90 degree. Sorry, the angle between them is 90. For a dot product, the angle, we take the angle of angle between magnetic field and ds as the cosine. So that's why cosine 90 is 0. Which means that the line integral of magnetic field for the second case is equal to 0. And here there is another whiteboard problem. Please work on it, and we will post the solution. And here there is a current distribution, and you will use Ampere's law to calculate inside of the current carrying wire, and you will also calculate outside of the current carrying wire what is the magnetic field inside and outside. So you will see that the Ampere's law is very helpful for those kind of problem as we did in the Gauss's law. Please work on it, and then we will post the solution. And now we will talk about application of magnetism. we had also learned there are many applications of electricity to create or to generate uniform electric field. And here we will also see there are many applications of magnetism to generate a uniform magnetic field. Uniform magnetic field means having the same magnitude and the same direction of magnetic field at every point within some region of space. So a uniform magnetic, up to now, what we have learned about magnetic field, they were not uniform. A uniform magnetic field is generated with a solenoid. This is an example of solenoid. It is a helical coil of wire, as you can see here, with the same current I passes through each loop in the coil. Solenoids may have hundreds or thousands of coils, and generally we call them as turn, and sometimes they are wrapped in several layers. As I said, since they have a uniform, since they create a uniform magnetic field, they are important. The magnetic field is uniform inside of the inside of the solenoid. Assume that this is the turns, or those are the loops for the solenoid. Inside of the solenoid, the magnetic field is uniform at every point. So outside of the solenoid, the magnetic field will be equal to 0 for an ideal solenoid. And we can easily find it by using Ampere's law. We can create a closed loop as in here, and then we can write the Ampere's law. Line integral of B dot ds is equal to mu 0 times I enclosed. And from here, when we do the calculation, we will see that right here it is equal to 0, but in the inside, the magnetic field will be equal to mu0 current n, which is the number of turns, divided by L, which is the length of the wire. And here, electromagnet is another application for magnetic field. And it is a solenoid with an iron core. We can also say that it is a type of magnet in which the magnetic field is produced by an electric current. And magnetic field disappears when the current is turned off. And so those are the electromagnets usually consist of wire wound into a coil. So that's why in the center there is a metal, which is iron. And those electromagnets increases magnetic field since the iron becomes a magnet when you pass through a current, through those coils. This is the end of this chapter. I mean, if you don't understand anything, especially for the right-hand rule, please send us an email. And please make sure that you solve all the whiteboard problems or anything peer-shared question on the slides. We will also post all those solutions for those questions. And at the same time, we will put some links to show how to apply those right-hand rule. So, as I said, still, if something is unclear, please join us during office hour, and then we can talk about over there, or we can create another video to make your understanding better. So good luck.